Hi, good morning. This is the fourth lecture in the series on Riemann integration. And today, in the last lecture, we proved Riemann's theorem criterion for integrability, alpha integrability or general ordinary integral. Okay. So, in this lecture, we will use this criterion to prove the integrability of large class of functions. And if time permits, we will also look at a very special example for Riemann-Stieltjes integral. Okay. All right. So let us start sharing as usual. Yeah. So let us quickly recall what we did was if f is a bounded function from a b to r and alpha is an increasing function on a b, then f is alpha integrable. If and only if for every epsilon positive there exists a partition so that u of p alpha minus LF p alpha is less than epsilon, right? So we want to look at some examples, and it will be good if you had gone through the first one or two lectures because we had already computed few. Okay, the first example, suppose if f is a constant function a to r and fx equal to c, okay, for all x, and of course alpha is increasing, then f is alpha integrable. Why? Because we had already seen that u of p alpha is for any partition p, the upper sum is going to be alpha b minus alpha a times c, and which is also equal to L of p alpha. Therefore, if I take the GLB of this and the LEB of this, I am going to get this, right? Therefore, the upper and lower alpha integrals coincide, therefore f is integrable. That's a very easy thing, right? Okay. Now let's look at a function which is continuous from a b to r. Let us assume it is continuous on a b. As usual, alpha is increasing. I want to know whether f is integrable, alpha integrable. Okay, and this is the best time for us to kind of zero on a strategy. See, what are we supposed to show to check integrability? If you give an epsilon, I have to find a partition p so that u of p alpha minus L of p alpha is less than epsilon. So let's try to write down u of p alpha minus L of p alpha. This has nothing to do with this continuity, etc. It's a very general thing. So what is u of p alpha minus L of p alpha? Okay, this is going to be something like mi minus small mi times delta alpha I. Do you understand this? So what do I want? I want this to be less than epsilon, right? I have to choose a partition p so that this should happen. Have you understood? Right. Now how do I achieve it? We are developing a general strategy for all cases. Okay, one way could be somehow if we can control this, that is the intuitively I am talking maximum minus minimum, which is same as LEB minus GLB. Okay, not same as, okay, that's what I mean by, if I can make sure this is less than epsilon, then this epsilon comes out, then what I will have will be, this will be telescopic sum. So I will have something like alpha b minus alpha a. Okay, so therefore I can just I can make sure that this is less than epsilon by this object, whatever. You understand this? So one way would be to choose a partition p so that this mi minus little mi is can be controlled better. I understood, right? Now the second thing is, there may be cases, whatever partition, okay, there may be certain points where things are very bad, therefore whatever partition P I choose, I may not be able to control mi minus mi. Do you remember our example? Here it was 10, and here it was 1, here it was 2, and at 0, right? So whatever small interval I have, there is no way I can bring it down to small 1. You understand that? So in such cases, the strategy is, okay, then this mi minus mi, this will be less than or equal to, in modulus, it will be less than or equal to 2 times m, where m is the modulus, let us say. This is not the same m, some other m, okay, or if you want to c, 2 times c. Yeah, this anyway, this will be less than or equal to 2m, because mi will be less than or equal to m, and mi is greater than or equal to m, right? Therefore it's greater, therefore minus mi will be less than or equal to minus m. Okay, anyway, so you understand this? So this will be bounded anyway. Let us say c maybe 2 by 2c, that's okay, right? Then what do I do? This c may be very large, like here 10 minus 1, or it may be 10 to the power 10 minus 1. Okay, then what do I do? Then what do I do is, I try to control this delta alpha I. That is, when your alpha is equal to x, the identity function, this is same as xi minus 1. That is, you try to make the length of this kind of intervals very small. That is, so you break it into two sums. Okay, I not equal to troublesome. Okay, then mi minus mi times delta alpha I. Okay, this can be controlled because this will be less than epsilon, therefore telescopic. Then these are troublesome. Okay, this will be bounded by something like c, okay, or 2c if you want, times delta alpha I. So I want this to be less than epsilon. Then what do I do? This is constant now, therefore I have to make sure, choose the partition x1, x2, xn, etc. in such a way that delta alpha i's can be controlled. And the total length, it's not only they control, because this is 2c comes out, therefore 2c times this total length, intuitively alpha length must be controlled. Have you understood? If you even vaguely understand, that's good enough, because when you see that's what we are doing, you will all of a sudden you will see, that's what the proof is. So you will understand that way, rather than just going through mechanically a proof and checking logic. Okay, let us go through this. Now let's look at this in, okay, let's look at this example itself. Instead of continuity, let me look at this example. F is from -1 to +1 to r, so that f of x equal to, let us say 1, 0, -1 less than or equal to x less than 0 equal to, okay, 1000 at x equal to 0 equal to 2 for 0 less than x less than or equal to 1, right? Now whatever partition you take, if my 0 happens to be in the thing xi minus 1 to xi, you see that this alpha is x, alpha x equal to x if you want. Okay, that's a function we are looking at. Okay, this is an ordinary Riemann integral is what I am looking at. Okay, then what do I know? Okay, here the distance is going to be 1000 minus 1. You understand that, right? Because capital Mi will be 1000 and small mi will be 1, therefore this will be 100 into length. So what is the idea? The idea is to make this length very small. Do you understand? Go back to our first lecture. I don't remember whether in the first lecture or second lecture we have achieved that. What did we do? We did that. So how to choose a partition? So I understand the problem is at 0, then I put it in -1 by n to +1 by n. Then what do I have? So my u f p minus LFP. Okay, this is, what are the nodes? 0, this is one node, this is second node, this is the second and third node, this is the fourth node. Sorry, -1 to +1, right? So on this upper and low, okay, little mi equal to capital Mi equal to 1. Here the same, mi equal to capital Mi equal to 2. Yeah, therefore what do I have? So this minus this will be 0, right? Summation m capital Mi minus small mi times 1 minus 1 by n, but this is 0. That's, and here this is going to be, here it is 1000 minus 1, therefore 999 times 2 by n. Yeah, and plus here again for the same reason, capital Mi minus small mi into 1 minus 1 by n. But this is 0, this is 0. Have you understood? Yeah, call it if you want Pn, right? Therefore this is whatever it is 9, therefore 1998. I hope I wrote it correct, by n. I want this to be less than epsilon, so it tells me I have to choose n, so that let us say 2000 by n, this will be easier for me, it will be less than epsilon. Yeah, can we do that? By argument property I can do that. Do you understand what I said now? So there is a place where I cannot control mi, capital Mi minus small mi. Then what do I try to do? Then I try to control delta alpha I or xi minus xi minus 1. Have you understood? Okay, please pause, review, proceed. Now let's come back to the continuity case and alpha increasing function, right? Then what will be u of p alpha minus L of p alpha? That is going to be summation mi minus mi times delta alpha I. Now what do you think you can do? Because of continuity, I have intuition that this can be made less than epsilon, right? I have xi minus 1 and xi. Remember, this is a closed and bound interval. Yeah, therefore this is a continuous function, therefore it attains its a maximum little mi and a minimum small mi. You understand? And I want the distance should be less than something like epsilon, or epsilon by something to do with alpha b minus alpha a or whatever. Yeah, so how do you think I can do that? So if the distance between them is small, but do I have any idea about where these points are going to be taken? This may be say Si, this may be a Ti, f of Si may be capital Mi, f of Ti may be small mi. Okay, if Si and Ti are very close to each other, then this will be very close. That's correct. But I do not know where Si, where Ti is going to be. But I know it has to be in the interval xi minus 1 to xi. That I can control. The length of this interval I can control. You understand this? And this has to be done everywhere. So what do you think I should do? Here continuity alone will not do. You understand this? Here also I have to do. Okay, so what do I do? So what I do is, since f is continuous and closed at bound interval, I know it is uniformly continuous. Right? Now what do I want? I want this to be less than epsilon. Okay, if you want I can write epsilon by something, but let's not pretend. I just want epsilon, capital Mi minus small mi to be less than epsilon. So what does it mean? By uniform continuity, I know there exists a delta positive, so that whenever s minus t, s and t are in AB, which is less than delta, should imply, okay, distance between fs and ft will be less than epsilon. Yeah, you understand this? Right. Now, so what do I do? So I can choose a natural number n, so that 1 by n is less than delta, not for 1 by n. By argument and property I can do that. Yeah, then what do I do? 1 by n, or even make it b minus a. Okay, let us say 1 by n is less than delta. You will see that I may have to modify slightly. Okay, we will do that because it's good, instead of saying, okay, there is, it will look mysterious. Let us do that. Okay, then what do I do? I take this interval a b and split it into n equal parts. Therefore what will be my xi? Xi will be a plus I by n times b minus a, and I run from 0 I less than or equal to n or capital N. right? Therefore my the distance between xi and xi minus 1 will be less than b minus a times n. You understand that? Therefore if it is b minus a by n, and that I want it to be less than delta, therefore what should I do? I should take here b minus a by n less than delta. Are you following? Choose n so that b minus a by n is less than delta. Therefore if I take any xi minus 1 and xi, this distance will be b minus a by n, but that's less than delta. Therefore if you take any 2 points si and ti, where f of si is the maximum, f of ti is the minimum, the distance will be less than epsilon because of this result. Have you understood? Yeah. Therefore what do I have? Therefore I have u of fp alpha minus L of fp alpha equal to summation mi minus mi into alpha b minus alpha e. Okay, I equal to 1 to. Okay, so for which partition? For the partitions which is so that AB is split into subintervals of equal length. What is the length of each of the subinterval? B minus a by n. How I chose my n? B minus a n less than delta. What is this delta? This delta is the one which correspond to the epsilon by the uniform continuity of f. Okay, good. So this will be less than, okay, this is alpha, sorry, delta alpha a. Okay, summation delta alpha a. But we know this is epsilon to alpha b minus alpha a. Yeah. So if you wanted here to be pure epsilon, what you would have done? You would have done by uniform continuity, choose delta so that this is less than alpha b minus alpha a. And remember again, you assume alpha is increasing, but what we actually meant is alpha is non-decreasing. So there is a, okay, suppose by bad chance alpha b equal to alpha a, then this may not make sense. Then you will take 1 plus alpha b minus alpha a. This kind of small adjustments by now you should be able to make. Have you understood? So what do you think I have proved? I have proved if f is any continuous function on a closed and bounded interval and alpha is any increasing function, then f is alpha integrable. What was the crucial idea here? The crucial idea was to use uniform continuity. You understood that? Because for this, if I use only continuity, then this delta will differ from when I come here. So I have to make uniform continuity. And second, do you understand the principle which I just said? Look at u of p alpha minus L of p alpha. Then, okay, how I want to say this sum is less than epsilon. How do I control that? Either I should try to control capital Mi minus small mi. These are the good points, good subintervals. Okay, on which I can. Or if any such subinterval is always a problematic, okay, troublemaker, then what should I try to control? I should try to shrink the subinterval. That is, delta alpha I should be small. Okay, in this case we achieved the second point. Okay, in this step function case, and whereas in this case we can see that all subintervals can be made nicely. Okay, please pause, review, proceed. Now let's look at the standard example. Okay, Dirichlet's function. What is the Dirichlet's function? F is from 0 1 to r, so that fx equal to 1 if x is in q and also in the domain, equal to 0 if x is not in q. Right? Okay. Now we want, and I am sure that all of you will remember what is LFP. LFP alpha is always 0. Yeah? Yes? Because minimum is 1. Whereas UFP alpha is, the maximum is going to be 1 into alpha xi minus alpha xi minus 1. Therefore, it's going to be alpha b minus alpha a. So if alpha b minus alpha a, if they are different, then what do I get? My u of p, u of alpha is 0, and sorry, L of f alpha is 0, and u of f alpha is alpha b minus alpha a. Alpha 0, sorry, alpha 1 minus alpha 0, because we are in the case 0, 1. In the case in alpha of x equal to x, this is same as saying equal to 1. So the lower integral is always 0, the upper integral is 1, therefore the function is not Riemann integrable. Provided alpha 1 is not equal to alpha 0. In particular, standard Riemann integral of this function does not exist. Okay. Right, now we'll come to the last example. There are a lot more examples, but this will be the most important example for Riemann stages. Most significant example. Okay, so let us look at I mean, for anything I can define, but let me do it. Okay, maybe I will do it first. Okay, suppose you fix a and b and a c in between. Okay, then we defined h sub c. It's called Heaviside function. Heaviside is the name of a physicist. So that hc, okay, of x is 0 if x is a less than or equal to x, x less than or equal to x, x is less than c, equal to 1 if c is less than or equal to x, less than or equal to b. Okay, there is a jump thing. See, here it is 0, and from here onwards 1. So is it clear that alpha is increasing function? Of course. Okay, now suppose f is a function from a b to r. Okay, I want to know whether f is alpha integrable. When is okay, either I want a necessary condition or I want a sufficient condition. If I am greedy, I want necessary as well as sufficient condition for alpha integrability of f. Is the question clear? Yeah. If you have gone through my second example, spend some time, understood, okay, you will have some kind of an idea how to deal with this. Okay, that's why I took the easy example first, so that you will understand it better. So what is the trouble point here? The trouble point is c, right? So what do you think I should do? See, here all of a sudden in any interval around c, okay, the left side is going to be 0, right side is going to be 1, my alpha. You understand? Therefore alpha xi minus alpha xi minus 1 will always be 1. Have you understood? So go back to my idea, what I said. Yeah. So what do you think I should like to control? I would like to control this one, delta alpha I. You see that? Now we even know how to attack the problem. It's not just because somebody gives a solution, I can understand the okay, it gives us independent way of arriving at. And so the way we do that, again, see, look at, unlike the step function which I did, something like 1,000 and 2, here you can see from c to b, including c, it's a constant. So that gives us some kind of an idea. Maybe I should look at a, c and B. C need not be midpoint or anything. It looks something like. So what I want is I'm looking for a partition P so that my xi equal to C. This is my xi minus 1 and this will be xi plus 1. You understand this? This is xi. That is, I'm looking for a partition so that my C is in the right end point of one of the partitions, one of the subintervals. Is it clear to you? The reason why I choose is because if I take any interval, then again 0 and 1 will be there, but here I can control. Here also the 1 will be there. Okay. Anyway, just don't worry, we'll go through it, we'll understand. Okay. So you understood how I chose the partition. Now let's look at what will be delta. Let me make it k then. K minus 1. This is k plus 1. This is xk. Okay. What will be delta alpha I? Delta alpha I will always be 0. If what happens? If I is less than k. Right? This is k. Now I take xi minus 1 xi. Okay. This I is less than k. Right? Therefore it has to be this. Right? Let us just see. Oh, I have done it correctly. Yeah. Right? This is alright. Okay. Do you understand this? Because alpha xi minus 1 will be 0, alpha will also be 0. Then let's look at what is will be delta alpha k. Delta alpha k will be alpha of C, that is 1, my alpha of k minus 1, which is 1. And what will be delta I if I is greater than k? If I is greater than k, okay, this is xk, which is equal to C. If I is greater than k, it has to be at least starting from k plus 1 onwards. Okay, therefore it's greater than C. Therefore xk plus 1, okay, xi will be greater than C. Similarly, xi plus 1 or x, both will be greater than C. Right? Therefore here both alpha at this point as well as alpha at this point are 1. Therefore delta alpha is 0. How many of you understand this? Spend some time, make sure that you understand. Okay, therefore what we have is the following. Therefore L F P alpha, where P is this partition, is going to be, okay, mk minus small mk times delta alpha k, which is 1, because all delta alphas are 0 and here, okay, for I not equal to k. At that point it is mi minus 1 plus delta alpha k, which is 1. Have you understood? Okay. Into, yeah, sorry, this is, I'm very sorry, it is UFP alpha minus LFP alpha. Okay, I'm sorry for the confusion. Is it clear? Because this is going to be summation mi minus mi into delta alpha I not equal to k plus mk minus mk into delta alpha k. And we know delta alpha k is 1 and we know all these are 0, therefore I get this. Okay, right. So now it's very clear. What do I want? I want this to be less than epsilon. And what are mk and mk? So let us look at it. This is my xk minus 1. This is my c, which is equal to xk. And okay, I want the maximum intuitively. Okay, when I say maximum, do not hold me. I know analysis. What I mean is LUV of this function on this interval and the GLV of this function in this interval. It should be controlled. What is the best way of controlling? Can anybody guess? So all these points are going to be here, right? So what is the best way of controlling? You will immediately say that if C is continuous, like in the last thing you will do, but I don't need it because the right side of C does not matter to me. So what I require is, can somebody guess? Yes, assume that f is left continuous at C, that is limit x tends to C minus from this side of fx equal to fc. Okay, from this limit, left limit exists and is equal to fc, then we say f is left continuous, right? Then is the result clear? Yeah. Why? Because since if this is left continuous, what do I know is, give me any epsilon. Now we can go back to our Riemann's criterion. Give me any epsilon, I have to find a delta, etc., etc., right? Oh, sorry, I have to find a partition, etc. So what I do is, since f is left continuous at C, for this given epsilon there is a delta positive, so that for all interval x minus C minus delta to C, okay, for all x here, what happens? Mod fx minus fc is less than epsilon. This is what left continuity means, right? Yeah. Therefore, for any x and y in the interval, okay, given delta, what do I do now? I find a partition P of AB in such a way that, okay, this interval xk minus 1 and xk which is equal to C, this is less than delta. You follow that? Therefore, for all xy here, what will happen? Mod fxy minus fy, okay, that will be less than or equal to mod fx minus fc plus mod fy minus fc, that will be less than, if you want, make it epsilon by 2, it will be less than epsilon. Okay, you follow that? Okay, so what does this say? If you want, you can also do in a slightly different way. Therefore, for all x in the interval k minus 1 to xk, for all x here, fx, what do I know, is greater than or equal to, greater than fc minus epsilon, less than fc plus epsilon by 2. I made it by epsilon by 2. Yeah. Therefore, what will be capital Mi? That will be less than or equal to fc plus epsilon by 2, and small mi, that will be greater than or equal to fc minus epsilon by 2. Therefore, okay, because I have to take GLB here and I have to take LEB there. Yeah, I hope you all of you follow. Please recall what I said. LEB, GLB, you should be very thorough, then only you will find it easy. Otherwise, every time you'll simply, yes, you may want to accept rather than you understand and then accept. Okay, is this clear? Therefore, the distance between them will be epsilon, right? So we are through. Have you understood? Please go through that. Okay, pause, review, proceed. So I want to see, this is a digression, you can ignore this, not required, because this already gives easily. Yeah, so you can also see that I am thinking. Okay, so what do you think I have proved now? Okay, alpha defined like this, I say f is alpha integral if alpha is continuous from the left at C. It's left continuous at C. Have you understood? You are sure? Okay, so this is a sufficient condition. That is what we have proved is, if f is left continuous at C, then f is alpha integrable. This is a very important example. Okay, we will again come back to this example, revisit it many times. Okay, right. Is the converse true? What does that mean? Suppose f is like this and I know f is alpha integrable. Do you think it should be left continuous? See. Yeah. So what does it mean? To show f is left continuous at C, what is our definition? Given an epsilon, I have to find a delta so that for all x in C minus delta to C, mod fx minus fc should be less than epsilon. Yeah, that's all I have to prove. How do you think I can do that? So you give me an epsilon, right? Since f is alpha integrable, assume f is alpha integrable. Okay, and let epsilon be given. I have to prove limit x tends to C minus of fx equal to fc. That means given epsilon positive, there is a delta positive so that x belong to C minus delta to C. Okay, fx minus fc in modulus should be less than epsilon. Is that clear? This is all I want to prove. Okay, good. Now let us go back. So what do you think I will do? Since you give me epsilon to check left continuity of f at C, okay, I know f is alpha integrable, therefore I can use Riemann criterion. What does the Riemann criterion says? Since f is alpha integrable, for there is a there is a partition P. Right? So then what happens? U f p alpha minus L f p alpha is less than epsilon. Is that okay? Now for any partition, okay, now notice that if this is true, it is true for any partition Q which contains P, so that C is a point of Q. See, Q is a refinement because this result is always true, right? Are you following me? Yes, because if Q is a partition, then U f Q alpha will be less than U f P alpha, and L f Q alpha will be greater than or equal to L f P alpha. Therefore negative will be less than. Therefore L f P alpha will be less than L f P alpha, but that's less than epsilon. Therefore this is true for every Q also. This, okay, I can replace this by Q. Now what is the advantage? I am taking this to be Q, right? Now let's go back. So what does it say? Now we have seen for such things we know how LFP UFP alpha minus LFP alpha looks like. It is only, let us assume my C is equal to xk as earlier, then it is going to be mk minus mk. That is less than epsilon. Okay, this implies mk minus small mk. We are assuming xk equal to C is less than epsilon. Yeah, you follow that? Okay, now what do you think I know? My C is lying there, therefore mk less than or equal to fx. So this is my mk, this is my capital mk, and I do not know where fx and, okay, this may be fx and this may be fc. Okay, they may lie somewhere here. They may not be less than or equal to, greater than or equal to something, but they are going to be somewhere here. You understand that? Therefore what is the distance between them? The distance is, yes, at most the distance between mk and capital mk minus small mk, right? That is less than epsilon. So what does it say? For each x in the interval xk minus 1 to xk, which is equal to c, for each x, my fx minus fc is less than epsilon. That means f is left continuous. That's c. Okay, please go through this. As you can see, I'm expecting those of you who are watching this or already have gone through enough analysis lectures by anybody, in particular my lectures on my video lectures, so that you are very comfortable with this way of thinking. So you can see I am going a little faster than usual. Okay, this is what I usually do in my classroom also. In the beginning I go very slow, prepare the ground, and students begin to think along with me. Then after that I just give a proof. Okay, you can understand. Okay, let's come back. So let us wind up the lecture. What do you think I have proved? What do you think I have proved? I have proved if f is left continuous at C, then it is alpha integrable. What is alpha? Alpha is the Heaviside function. Something interesting, did you notice? How many of you noticed something interesting in this example? Yeah. Did I ever use alpha is increasing? Right? It could have been any function, right? Alpha is a Heaviside function, is fine, and we also saw it's increasing. What did I use? The fact it is increasing in the proof. Check. Okay. Have a good day. We'll stop the lecture with this.